Hello, and welcome to this video introducing us to systems of equations. As always, give this video a thumbs up if you find it helpful, subscribe to the channel for more math help, and be sure to check out some of the other playlists and videos on the channel to help you out in whatever math class you are taking. So as I was planning out this lesson, my intent was to just jump into solving systems of equations. And as I looked at the first lesson, looking at the first strategy, I thought, ooh, if you've never done this before, you might not even know what a system is. So we don't know what a system is. We don't know what we're doing when we're solving a system. And to cram all that into one lesson makes for a very, very dense lesson. It also means that if you jump ahead in the lesson, so you're looking for help with a particular strategy, that you would miss a key part of that. So I wanted to try to break this down into maybe some shorter lessons and lay the groundwork of what on earth we are doing before we get into how are we going to do this. Now, systems of equations are sometimes called simultaneous equations. This is a little bit older term. I don't hear it a whole lot in the math circles that I run in, but you will see it on some calculators. So it's possible that you'll have a calculator that in one of the menus for the calculator, you'll see something that looks like this. It might say simultaneous, but that's a long word. So a lot of times you'll see simult, okay, and you're playing around, you got a brand new calculator, it's got all these cool menus on it, and you see simult on it. That means simultaneous, and it means that that calculator has some sort of function on it that will allow you to solve these systems. So you will see that vocabulary, and I want to make sure that I cover that in case you do, or in case you have a textbook or a teacher that's using that vocabulary. Now, what a system of equation is, it's two or more equations with two or more variables or unknowns. So up until this point, we have been working with strictly one equation at a time. So maybe it's an equation like this, 2x plus 1 equals 5, and we are told to solve it. And there's one variable in it, in this case, an x, okay, and you're solving for the x. Or we might have seen one equation in two variables, and we might be asked to graph it. And we've looked at what solutions are in both of those scenarios with one and with two variables. But a system of equations, you're actually dealing with more than one equation and more than one variable. So here are some examples. We have two equations with two unknowns. So we'll take a look at this. So we have two equations right here, 2x minus 3y equals 5 and 4x plus 5y equals 7. And I'm still in a weird situation in my apartment, so you are hearing a cat. I apologize for that. But this is a system. It's got two equations, and there are two variables, the x and the y. This is an example of what we call a 3x3 system, meaning it is three equations with three unknowns. So in this system, we have an x, a y, and a z, and we have three equations. Now, you'll notice that the last equation does not have the z in it, and that's actually okay. It just means that in this case, if you were to write it with the z, it would look something like this: negative 5x plus y plus 0z equals negative 1. And that is actually okay to have. So you've got three variables in there, an x, a y, and a z, and three equations. So those are examples of systems. Now, key fact about systems: in order to solve a system, we need to have as many equations as we have unknowns. So for example, if you have two variables, you need two equations. So I have told students this before. If somebody, sorry, there is a cat wanting to be a part of this lesson. And I don't have my camera on. Years ago, I had other cats and I would have my camera on. And so they made regular appearances in my videos. I haven't had my camera on. You're just gonna have to take my word for it that I've got a cat. Okay, so I've told students that if you saw something like this and somebody asked you to solve that, and that was all the directions you were given, not solve for x or solve for y, it just solve, that you can't do it because there are two variables there with in just one equation. So there's actually an infinite number of solutions to that, as we saw when we were graphing lines. There's an infinite combination of x's and y's that can make that equation true. So if you wanted to find the actual values for x and y, you would need to have two equations that have the x and the y in it. So for example, this is not solvable right here. So if we look at this, our first equation has an x, a y, and a z. So that establishes this as having three unknowns. Now the second equation only has an x and a y, which is fine. We mentioned that on the previous slide that we don't need to have the z there, but I do need to have three equations. So this particular system, I might be able to get partway there, like I could eliminate one of my variables, or depending on what strategy we were using, but there is no way I can solve this for x, y, and z. I don't have enough information. So in order to solve a system, you do need to have as many equations as you have unknowns. Now, what does it mean to solve a system? I've kind of been tossing that out there. We're talking about solving a system, and you might be able to figure this out on your own. Recall that a solution to an equation is a value of the variable that will make the equation true. This is one of our foundational key ideas. When I am going through the concepts of algebra, there's certain ideas that I'm like, this is a key idea. And one of those key ideas is that the solution is the value of the variables that will make the statement true, whether the statement is an equation or whether the statement is an inequality, or in this case, it's going to apply to a system. We're always looking for values of variables that will make something true. Okay, so you want to have that key concept down rock solid. Therefore, the solution to a system is the values of the variables that make all of the equations in the system true. So it's not enough for it to make one of the equations true. You need to find the values of the variables that are going to make all equations in the system true. And what I want you to note there is how this definition is not really different from this definition. So if you know what a solution is, it will apply across all of your math, even when we put some like twists and turns in the way. So let's see what this means. Okay, we're going to just look at an example here to see what it means. Determine if 0, 1, and -2, -3 are solutions to the system shown below. So here's my system. I have two variables, an x and a y, and we'll go ahead and we'll check the point 0, 1, or the values here. We're going to test x is 0 and y is 1. And we want to see if these values of these variables will make all of the equations true. So looking at that first equation, we've got -2 times 0 plus 1. -2 times 0 is 0, and 0 plus 1 is 1, giving me 1 is equal to 1. So it works for the first equation. But remember, for it to be a solution to the system, it has to make all the equations true. Okay, so we're going to look at that second equation and plug it in. So we're going to plug in x is 0 and y is 1. 3 times 0 is 0, and 0 plus 1 is 1. And I end up with 1 equals -9, which is not true. And so no, 0, 1 is not a solution to the system. Now, you could say it's a solution to the first equation, so that point 0, 1 makes that equation true. So if I were to graph that, the point 0, 1 would be on that graph, kind of file that information away. But it does not make the other equation true. So it's not a solution to the system. Let's take a look at the other point. So we're going to look at -2, -3. So in this case, we're going to plug in x is -2 and y is -3. That a little bit clearer. There we go. So looking at this first equation here, we're going to plug in -2 and then a -3. -2 times -2 is +4. And +4 minus 3 is 1. And so it does work for the first equation. And we've got to check it on the second equation as well. So 3x plus y is -9. And we're plugging in x is -2 and y is -3. 3 times -2 is -6. and -6 minus 3. Now, it might help you here. I do this all the time, or I say it might help you to think of that as plus negative. So -6 plus -3 is indeed -9, making both of them true. And so, yes, -2, -3 is a solution. And just a heads up, this will often trip up my own students when I do this. SOLN is a fairly common abbreviation for the word solution. Just means we're a little bit tired of writing the entire word out. Okay, and that's what it means to be a solution. So you're looking for the values of the variables, in this case, the values of both x and y, that are going to make all of the equations in that system true. In this case, this is what we call a 2x2 system, meaning it's 2 variables and 2 equations, and it has to make both of the equations true. So how do we solve systems? And this is where I've been doing this for about 11 minutes now, and I didn't want to front load all of that and then also put the strategies into a video. That's going to make for a way too long video and too much content in there. So there are several strategies. The first strategy is graphing, okay? And we're going to explore a lot of these strategies in upcoming videos. Now, here's the deal with graphing. Graphing works well for lines, which is the focus of our study in Algebra 1. Algebra 1 is dominated by a study of lines, and solving systems by graphing lines is actually not too bad to do. It does require usually some graph paper and a ruler to make sure that it's going to work, but generally lines aren't too bad. If you have graphing technology, it works well for all systems that have 2 variables, including systems that do not involve lines. So we really start our study of algebra off with lines, but as you move into the latter parts of Algebra 1 and into Algebra 2, then you'll have other kinds of graphs that are not lines. Well, as long as you're limited to X's and Y's and you have access to, say, a graphing calculator or to Desmos, then you will be able to use graphing really well. And Desmos can employ a graph to solve for up to 3 variable systems, and that involves the use of something called a slider. It's kind of cool to do, but you can figure out how to use Desmos to graph, and then like the third variable is done on the slider. Second strategy is substitution. This is perhaps the most intuitive method to do by hand. When I was learning how to solve systems, substitution was the one that I preferred. It just made sense to me why the strategy worked. And when something makes sense to you, you're likely to not forget it. So you want to be able to remember it. Next one is sometimes called adding. I've seen it called adding or subtracting. You'll also see the term linear combinations. This one is perhaps the cleanest method to do by hand, meaning that if you do this method right, you can avoid a lot of fractions and kind of messy substitutions. So the substitution method can get pretty messy. This method is actually pretty clean. What is more challenging about it is it does require some pretty good number sense because you have to make decisions about how to do multiplication in that. Matrices. Matrices are beyond the scope of Algebra 1 and often beyond Algebra 2 as well. I learned matrices for solving systems in an Algebra 2 class, but I've also taught plenty of Algebra 2 classes where we don't touch it. But they're kind of fun. They're a unique way of being able to solve systems and will sometimes work well for systems that have a lot of variables in them. And calculators, I have to add this, an increasing number of calculators have the ability to let you type in the equations and just generate the solutions. I mentioned earlier, you might be tinkering around with a graphing calculator and you'll see a menu option that says Simult, and that means that that calculator probably has a way to do it. Now, it doesn't get you out of knowing all the math because usually when you input the equations, you've got to input them in a particular form in order for the calculator to read what you're going to do. But I've had one of my favorite scientific calculators actually will do up to 3 equations with 3 variables. And that's the scientific, it's not even a graphing calculator. So increasing number of calculators have the ability to do it. So what's an example of a systems problem? Now I'm going to be really honest here. A lot of the examples you find in math books are ridiculous. They are just ridiculous examples. They help you practice the mechanics of solving systems, but they are not remotely realistic. They would be things like you're going to an amusement park, and if you have 6 adults and 3 kids, the cost is, $150. If you have 2 adults and 5 kids, the cost is like $200. Find the price of a children's and an adult ticket, and it's ridiculous because nobody would ever do that. Like, you would just go online and look at the price for an adult and like a student ticket or children's ticket. So they help you practice the mechanics of solving the system, but they're not any kind of realistic situation. Now, there are plentiful real life examples, but they are often contextually complicated and they just don't work well in a classroom setting, especially when you're just learning the strategies. One of the worst systems I ever saw was in college. It was in a mechanics class, which is a kind of physics class, and it was 7 equations with 7 unknowns. And what the problem was like a volleyball net that was on a beach, and so like the ground was tilted, and you had these wires balancing the volleyball net, and you had a point, and then there were all these forces at work. So you had one wire pulling this way and one wire pulling this way, and the net was pulling in 2 different places, and each one of those forces was an unknown, and we had to figure out, like, I don't actually remember what we had to figure out, but we had to figure out what all those forces were to determine whether or not the volleyball net was actually going to stand up or whether we needed more reinforcements. So, I mean, that is a fantastic real life example, but it's really complex and it's not great to use in a classroom if you're just learning how to solve systems. I've also sat down with financial advisors that talk about different options for investments, and you're staring at a system and you need to figure out what's the best way to allocate money between funds. Also fantastic real life example, but contextually complicated. So it's not something that you'd want to use in a classroom because spend so long trying to understand the context that you'd never get to the solution. So here's one okay-ish scenario, just okay-ish. Stefan is trying to choose between 2 international calling plans for an upcoming trip. The first plan costs $50 to join, and then $1 per minute for each minute he talks. So to join that first plan, he's going to give the company $50, maybe get a calling card, maybe get a code. And then as he is traveling, for every minute that he talks and tries to call back home, it's going to cost him $1. The second plan costs $75 to join. So this is going to cost you more upfront to join, and then 50 cents per minute for each minute he talks. So he can pay more money to join up front, but he's going to save money each minute that he talks. After how many minutes of talk time will the 2 plans cost the same amount? Okay, and this would be like an okay-ish problem. You want to find out, when are these 2 plans the same amount of money? Stefan might want to know that if he has an estimated idea of how long he might talk, to see whether or not which plan he wants to get. So try to work this problem out using any reasoning you can, and then comment your answer below along with a brief description of how you found that answer. So what number did you come up with? Now, I am going to give the number later in the video, so pause the video now, try to figure it out, see what you can do with it with no coaching or instruction. Can you figure out how many minutes it would be? And then comment that below and tell me, how did you figure it out? All right, don't forget, like this video if you found it helpful, subscribe for more math help, and check out the other videos on the channel. Wait for the next slide if you want the answer to the previous problem. And the answer is 50 minutes. So 50 minutes is when those 2 plans are the same. Were you able to get it correct? If so, how? Again, share it with me in the comments. If you got it incorrect, actually, that is more valuable than getting it correct because it gives us an insight into how we're thinking. So you know what? Share that too. And I will see you in the next video.